This is more for me to learn and review for my final, more so than it is to try and teach, so I apologize if I get stuff wrong along the way. But let's talk real quick about polarizing and polarization of a dielectric. So focusing on the dielectric part, basically if you take an atom that has a positive nucleus and a bunch of negative charges floating around, and you introduce it to an electric field, you have some sort of electric field here of some magnitude, doesn't matter right now. What's going to happen is the positive charge is going to flow with the electric field, and the negative charges are going to flow against it. And then you'll get something like this atom here, where you have your positive charge up here, and then all your negatives are kind of more towards the bottom in this case, right? So that's kind of the idea here. And so what we're looking at is we have a positively charged area and a negatively charged area with some distance between them, and the electric field is flowing that way. So what that leads us to is the first formula, which is, okay, yeah, cool. So our first equation is that our D field is equal to our emissivity times our electric field plus the polarization field. So this is polarization, and then this is electric field, and this is, I want to say it's permittivity, not emissivity, sorry. And that's of free space, because it's not. Okay. Okay, so one thing to note is that E of 0, E sub 0 is equal to 8.854 times 10 to the negative 12th. I believe it's farads per meter squared. Let me double check. Yeah, farads per meter squared, cool. And then of note in electronic devices, this is just a side note, we use 8.854 times 10 to the negative 14th farads per centimeter squared. Just a small little difference that we use for devices a lot. Neither here nor there. And then we'll use E of R from a table. Okay, here we go. Dielectrics. Okay, so the breakdown voltage, this is what I needed. Breakdown voltage is equal to the dielectric electric field, which is from the chart, and then multiplied by D, so the distance, right? So let's consider this this same dielectric here, basically, with a height D, right? And that has, it's operating at 60 voltage. It has a distance of 0.01 millimeter, and it's using quartz as its dielectric. Dielectric. Okay. The E sub R of quartz is 30 megavolts per meter. Yeah. So all we have to do to calculate our breakdown voltage is we're going to take VBD, and that's going to be 30 mega is times 10 to the 6th. Oh, yeah, 10 to the 6th, cool. 10 to the 6th volts per meter. We're going to multiply that by our distance, because we know we want a voltage. We have meters, so we have divided by meters, so we're going to multiply by meters. That's the other way to double check your formulas. We also know it's here, of course. Now this is 0.01, and then millimeters, so times 10 to the negative third. So what we can do is we can deal with our powers first. So what I'm going to do here is make this 1, because I don't want to use a calculator if I don't have to. That's kind of the deal. It's good to practice your algebra. So if I'm moving this over twice to make this bigger, that means the power gets smaller. So I have 10 to the negative 5. And then if I move this power, or this over to the left one, the power gets smaller, so it's a bigger negative is what I should have said here. So moving this one over, the power does actually get bigger. So I have 3 times 10 to the 7th. And then I know I have volts times meter divided by meter. And so now I can just calculate this out. Multiplying 10 to the 7th, 10 to the negative 5th is 10 to the 2nd. So I have 3 times 10 to the 2nd volts, which of course 10 to the 2nd is actually just going to turn this into 300 volts. Or if you prefer, you could write it as 0.3 kilovolts, but that's not a normal convention. 300 volts makes more sense. And so that's our breakdown voltage. So because this dielectric is going to break down at 300 volts, so voltage of breakdown is 300 and voltage of op is 60, which 300 is not only greater than 60, well, I guess it's not an order of magnitude greater, so it's just greater. In this case, since it's just greater, then we're good. This is operating within range, within acceptable range.